While studying kinematics, we saw that we could use math to predict the motion of an object. We could figure out where it has been in the past, where it will be in the future, how long it took to get there, and even how fast it was traveling. What we were really doing was analyzing how an object was moving. But why was it moving in the first place? In other words, what is it that causes an object to speed up? The answer is surprisingly simple. The only thing that can cause an object to accelerate is a force. In this video, we'll look at how forces influence the motion of different objects, and we'll challenge our intuition of how things work in the physical world. Here is a wooden apple, resting on a countertop. Before seeing anything else, you've probably made a number of assumptions. We rightly think that the marble counter is heavy and rough, and that the apple is smooth and light. Say we plan on giving the apple a shove to the right. We all have an idea of how the apple will slide and stop. And thanks to our intuition, we can make predictions like this on a moment-to-moment basis without much effort at all. But what if it were possible to remove everything that our intuition is based on? What if we could remove all the air in the room, which can cause air resistance? Remove all the friction from the ground and walls, and remove the force of gravity. Now if we pick the apple up and let it go, it won't move anywhere because there's absolutely no forces acting on it. If we bump the apple now, would it ever stop moving? The truth is, once we give the apple a bit of velocity, it stays at that velocity, moving in a straight line until it's bumped again. This isn't just an imaginary experiment. It turns out that this is exactly what happens in outer space. But before we go any further, let's look at a little history.
Sound travels at about 760 miles per hour, or 340 meters per second. That's about 661 knots on an average day at sea level. And sometimes you can almost see it. Going close to that speed through air can cause some unusual visual effects. What you're looking at here is a NASA image of an SR-71 bending light waves from the pressure differentials it's producing. Air's pressure and temperature both drop when airspeed increases. Rapid changes in density can be enough to bend light like a lens. How does it happen? Airspeed increases as it flows over the form of an aircraft pushing its way near Mach 1, the speed of sound. That means that even aircraft slower than the speed of sound can accelerate the air moving over them beyond the speed of sound. As pressure all around the aircraft drops, that air cools. And as air cools, its ability to hold moisture drops. So if there's enough moisture, you'll see it form in clouds that appear attached to the aircraft itself. But the cone-shaped clouds you see aren't in fact traveling with the aircraft. Each section of air is spontaneously reacting to the temperature and pressure change induced by the aircraft's body sliding past. Then there are the shock waves. Shock waves are formed by the air that can't get out of the way fast enough, forming a pressure wave. We perceive that pressure wave as sound. Aircraft actually usually produce two booms. They just reach us so quickly in succession that we can't distinguish the two. All of these factors are quite normal and have come to be expected in images that capture supersonic, transonic, or even near supersonic flight. But on rare occasions, we do get a glimpse of something special. At Kennedy Space Center on February 11, 2010, an Atlas rocket launched into ideal conditions for showing off shockwave. And this is the result. We hope you've enjoyed this little